This is first lecture on matrices. So you remember a vector in Rn is a column vector. One column of n numbers. An M by N matrix in Rn is it's not a column, it's a rectangle with M rows and N columns. So it's like each column is a vector. Let's say this is A11, A21, A31, down to AN1, that's an N vector. Sorry, M. It's an M dimensional vector. So it's like you have M vectors. Sorry, you have N M dimensional vectors. So this is A12, A22, A32 down to AM2. In general, if you have row I and column J, in the jth column, the entries are A1J, A2J, down to AMJ. And in this box, which is the row I, column J entry, the subscripts are AIJ. When you get to the last column, this is A1N, A2N, down to AMN. So this is what a matrix is. It's just a rectangular array of numbers. So for example, a 2 by 3 matrix might look like this. 2 rows, 3 columns. 7, 2, 3 minus 8, square root of 5, e squared. Right? These are just numbers. This is 2 rows, 3 columns. That's a 2 by 3 matrix. So a matrix is just a rectangular array of numbers. And if M equals N, let's say a 2 by 2 matrix, this is called a square matrix. Just the way a square is a rectangle where the height and the width are the same, square matrix is just a rectangular matrix which has a square shape. The number of rows equals the number of columns. Here you have the number of rows equals the number of columns. Here you have 2 rows and 3 columns. A 3 by 2 matrix would have 3 rows and 2 columns. Right? So this is a 2 by 3 matrix, a 3 by 2, and a 2 by 2. The first number is always the number of rows. The second number is always the number of columns. So it's just some numbers, nothing, no big deal. And if matrices have the same shape, that means same number of rows and columns, then, for example, you have matrix addition, you can add them. You know, like 2, 5, 7, 3, 0, minus 9. This is a 2 by 3. And here I have another 2 by 3. 1, 3, 21, 7, 0, 7, 4, 0. You add matrices just the way you add vectors, component-wise. So 2 plus 1 is 3. 5 plus 3 is 8. 7 plus 21 is 28. 3 and 7 is 10. 0 and 4 is 4. Minus 9 and 0 is 9. So this is matrix addition. You can also subtract. I took the same 2 matrices and I subtracted them. I just subtract coordinate-wise. 2 minus 1 is 1, 5 minus 3 is 2, 7 minus 21 is minus 14, 3 minus 7 is minus 4, 0 minus 4 is minus 4, minus 9 minus 0 is minus 9. And you also have scalar multiplication. If I have a matrix, and I want to multiply it by a number like, I don't know, 3. You just multiply every coordinate by 3, just as in scalar multiplication of a vector, you multiply every component, every coordinate by the scalar. So if I multiply this matrix by 3, 3 times 2 is 6, 3 5s are 15, 3 7s are 21, 3 3s are 9, 3 times 0 is 0, 3 times minus 9 is 27. So that's the simple algebra of matrices. You only can add matrices of the same shape. If you wanted to add 1, 2, 3, 4 to the matrix 5, 6, 7, 8, 9, 10, 11, 12, 13, that's impossible. They don't have the same, they don't have the same shape. This is 2 by 2, this is 3 by 3. They're not the same, so you can't add or subtract them. Now, matrix multiplication is more interesting. Let's just take a simple case. By the way, a vector 3, 2, 1, 0. This is a matrix. So this vector, it's a matrix with 1 column. In this case, this is a 4-row times 1. This is a 4 by 1 matrix. And if I look at a row vector, 7, 0, minus 3, 5, this is also a matrix with 1 row and 4 columns. That's a 1 by 4 matrix. And there's a way to multiply a row vector into a column vector if the number of rows here equals the number of columns here. And it's basically the dot product that you might have learned in calculus. You just take multiply the coordinates and add. 7 times 3 is 21. 0 times 2 is 0. Minus 3 plus 1 is minus 3. 5 plus 0 is 0. You get 18. So that's sort of multiplying a column vector, a row vector, or a row matrix, into a column vector. And again, the important thing here is the number of rows, the number of columns on the left equals the number of rows on the right. And that is the condition for matrix multiplication. So if you had, if A is an m by n matrix, and B is an n by p matrix. So mn and p are any positive integers, but here n is the number of columns of A, and here n is the number of rows of B. So if the number of columns equals the number of rows, then there's a definition, a construction of matrix multiplication. So for example, suppose A is a 2 by 3 matrix, and B is a 3 by 4 matrix. So A looks like, I'll make it easy, 1, 2, 3, 4, 5, 6. And let's say B is, this is 2 rows and 3 columns. Make some numbers. 3 rows and 4 columns. 2, 0, 1, minus 1. 5, 1, 2, 3, 0, 4, minus 1, 2. So this is a 2 by 3, and this is a 3 by 4. And when you multiply an m by n by an n by p matrix, the product AB, let's call it C, will be an m by p matrix. It'll be like the n's cancel. So this is 2 by 3. This is 3 by 4. The product, cancel the 3's, is going to be a 2 by 4 matrix. 2 rows, 4 columns. And the way you get that is, if you want to know, here, like the different boxes, you put in the numbers. This is row 1, column 1. Take row 1 and multiply it into column 1. You get 2 plus 10 plus 0. For the first row, second column, you take the first row and multiply it by the second column. You get 0 plus 2 plus 12. For the first row, third column, this first row into the third column, multiply them, you get 1 plus 4, that's 5, minus 3 is 2. And to get the first row, fourth column coordinate of this matrix, first row into the fourth column, 1 minus 1 plus 6 is minus 5. Sorry, minus 1 plus 6 is 5, plus 6 is 11. And we get the second row, it's the second row of this into the 1, 2, 3, 4 different columns over here. So for the second row, first column, 8 plus 25 plus 0 is 33. Second row, second column, 0 plus 5 plus 24 is 29. Second row, third column, 4 plus 10 is 14, minus 6 is 8. And finally, second row, fourth column, this coordinate, minus 4 plus 15 is 11, plus 12 is 23. And in the homeworks, you will have a lot of practice multiplying matrices. The most important special case for us might be, suppose you have 1, 2, 3, 4, 5, 6. So this is 2 rows and 3 columns. Suppose I take a 3 by 1 matrix. That's a 3-dimensional column vector. Let's just write it as x, y, z. When you multiply this, you're going to get a 2 by 1 matrix. What do you get? Column into row. Sorry, row into column. This is x plus 2y plus 3z. Row into column, you get 4x plus 5y plus 6z. Coordinates can be variables, numbers, anything in the matrix. Now, this is particularly important as a way to efficiently write down and solve systems of equations. So this may look a little bit silly, but suppose you had 6x1 plus 2x2 minus 5x3 plus 7x4 equals 19. The way you might write this down as a matrix is if you take the row vector, which are the coordinates, 6, 2 minus 5, 3, and write the columns, the variables as a column vector. This is a 1 by 4 matrix times a 4 by 1 matrix. The product would be a 1 by 1 matrix, which is just a number, and it's 19. Because if you multiply this row into this column, you get this equation, or you get this as like a 1 by 1 matrix. So if you have something like 3x plus 2y, 4x plus 9y equals 7 equals minus 9. Here we have a system of two equations and two variables. We can use the coordinates of the variables on the left-hand side, make that a matrix. 3, 2, 4, 9. Write the variables x, y as a column vector. If you do this matrix multiplication, what you get is 3x plus 2y, 4x plus 9y. And to say you're looking for a solution of this set of two equations and two unknowns is the same as saying you want to solve this vector equation. This means two vectors are the same, they have the same coordinates, so this means 3x plus 2y equals 7, 4x plus 9y equals minus, make this a 3. 4x plus 3y equals minus 9. So here I have equations written as equations, and this is the vector form for the same system of equations. Actually, I should write it like this. The vector form is 3, 2, 4, 3. That matrix times the vector xy equals the vector 7 minus 9. So this matrix statement is exactly the same as these two equations and two unknowns. It's just a different notation. So this is the short and simple thing to see in this exercise, in this little lecture. We have matrices, and they're very important in many, many, many different applications. And if you have matrices of the same shape, you can add and subtract them. You have a matrix, you can always multiply it by a scalar, and you can multiply two matrices if they have the same number of rows, if the number of columns on the left equals the number of rows on the right. Now, I should also explain what Gaussian elimination translates into when you have matrices. So you remember we have 3 elementary operations on a system of equations. First, you can interchange 2 rows. Second, you can you can interchange 2 equations. Second, you can multiply an equation by a non-zero scalar, and then you can add a multiple of one row to another. So for example, if we're looking at this system of equations, 3x plus 2y equals 7, 4x plus 3y equals minus 9. I could, for example, multiply the first row by a third. I would get x plus 2/3 y equals 7/3, and 4x plus 3y equals minus 9. And then I could take the first equation, I'm not going to change it in this step, but I can multiply this equation by minus 4 and add to the second equation. So we get minus 4x plus 4x is 0x. I get minus 8/3 plus 3, which is 9/3, so I get 1/3 y, and minus 28/3 minus 9, minus 4 plus minus 4 times it, 9 is 32 is 27 over 3. So I have minus 28 over 3 minus 27 over 3. I think that's minus 55 over 3. So I have this system of equations. Let me multiply the second equation by 3. So I have x plus 2/3 y equals 7/3, and y equals minus 55. If I add minus 2/3 times the second row to the first row, this is still y equals minus 55. I have x, 2/3 y minus 2/3 y cancels, that's just 0. And I get over here 7/3 minus 2/3 times minus 55. Let's see. 2 times 55 is 110. 110 plus 7, 117 over 3, which I believe is exactly 39. So by Gaussian elimination, we found that the solution of this system of equations is xy equals 39 minus 55. Let me just check. 3x plus 2y, that's 3 times 39 plus 2 times minus 55. 3 times 39 is 117, minus 110 is 7. That checks. 4 times 39 plus 3 times minus 55. 4 times 39, I think, is 156. 3 times 55 is 165. 156 minus 165 is minus 9. So good. We did find the solution. Using Gaussian elimination on the system of equations. But now, how can we do this using matrices? So we saw for these two equations, the matrix form was 3, 2, 4, 3, applied to the vector xy equals 7 minus 9. So this is the system of equations written in matrix form. And I want to write down what is called the augmented matrix. So we have the matrix of coefficients of the equations, and I want to augment or add to it by adding a column, which is the right-hand sides of the equation, 7 minus 9. And I want to use the augmented matrix of the system of equations to solve the system. How? How do we do that? Well, just as we had elementary operations on a system of equations, every elementary operation on the system of equations corresponds to an elementary row operation on a matrix. So the first elementary operation on a system of equations was you could interchange two equations in a matrix that corresponds to interchange any two rows. Just interchange them. Multiplying an equation by a non-zero scalar is the same as multiply any row by a non-zero scalar. And adding a multiple of one equation to another would correspond to add a multiple of one row to another. So let's see, what did I do for my equations? The first thing I did was I multiplied the first equation by a third. So let me multiply the first row by a third. I get 1/3, 2/3, 7/3. Oops, that's not what I get. When I multiply 3 by a third, I get 1. If I multiply the first row by a third, I get 1, 2/3, 7/3. And I haven't changed the second row at this point. Then I'm not going to do anything to the first row, but I can subtract 4 times the first row from the second row. So then the matrix becomes 4 minus 4 is 0. 3 minus 8/3 is 1/3. Minus 9 minus 27 minus 21/3. So this is minus 27/3. Sorry, minus 28/3 is minus 58/3. We get that matrix. If I, actually, let me just not change the second row at this instant. But let me subtract twice the second row from the first row. Again, 1 minus 0 is 1. 2/3 minus 2/3 is 0. 7/3 minus 110/3. Sorry, 7/3 minus 110/3 is 7/3 plus 110/3. 7 and 110 is 117/3. Okay. I'm not going to change the first row now, though I will notice that 117/3 is 39. If I multiply the second row by 3, I get 0, 1, minus 58. So by these elementary row operations on the matrix, I got a matrix which looks like this. And let me translate this back into equations. 1 times x plus 0 times y equals 39, x equals 39. 0x plus 1 times y is minus 55. Let's write these things down correctly. Y equals minus 55. So what I did just now was, first I solved the system of equations using Gaussian elimination. And then I translated the elementary row operations of Gaussian elimination into elementary operations on a matrix. Given a matrix, you can interchange 2 rows, multiply a row by a non-zero scalar, add a multiple of 1 row to another. And I picked a clever sequence of elementary row operations. So my matrix, in the end, ended up in this very simple form. The 2 by 2 part is just 1, 0, 0, 1. This is what's called the identity matrix. And that corresponds to the system of equations, and I solved the equations. So this is kind of an overview of the use of matrices in solving a system of linear equations. And I'm going to go through this in the next couple of lectures, just basically more and more examples of this. Because this is a central topic in linear algebra. That's all I needed to say right now.